Hello, everyone. My name is Elahe Ghalebi, and I'm going to talk about this joint work with Bahar Mirza-Soleiman, Radu Gursu, and Yure Leskovic. You may have heard of networks with wide-ranging applications, and they are often growing. For instance, new users join Twitter, and they follow each other. This adds new vertices and edges to the underlying network over time. There has been a lot of efforts modeling these dynamic networks. However, the efficacy of these models relies on obtaining full observations over the underlying network. But in real life, we cannot observe the whole structure. For example, social media companies are unwilling to share their topological structure due to privacy concerns and regulations. What's often known are the partial observations of the stochastic cascading process over the underlying network. A cascade is created by a contagion, such as a social media post, a virus, or a rumor that starts from some vertex of the network and then spreads like an epidemic from one vertex to another through the unobserved edges. For instance, epidemiologists can observe when a person gets sick, but they cannot tell who infected her. Therefore, the main question is, can evolving networks be inferred and modeled from these partial observations? We introduced ferns, a generative probabilistic model that is able to identify the underlying time-varying network. What we do is that at step 1, we extract observations from the diffusion data. In each cascade, the first infection times of each vertex is observed. Any two vertices that have increasing infection time can introduce an edge. For example, at cascade 1, vertex D could have been infected through vertex A or E. E of C is the set of edges that could have been involved in the transmission. In the first round, we calculate the probability distribution over the edges of each set. We calculate the marginal probability of every edge in the set, and we sample Q edges from this marginal probability, and we add them to the set of observations. At step 2, we provide the extracted observations to the model and update their probabilities using a collapsed Gibbs sampler. Here we use the model of mixture of Dirichlet network distributions to model the edges. For the next round, we get the updated probabilities for every possible edge in the network. We repeat the calculation of the probability distributions of each edge in the sets, and we sample again Q edges from these marginal probabilities of every edge. Then we update the model with the new set of observations, and we iteratively repeat the rounds until it converges. For the online inference setting, we discretize the time into equal time intervals. At each time interval, we only consider the infection times of vertices at that time interval, and we update the model using the observations in current interval. This way, we make sure that the edges that have been recently observed get higher probability. We applied difference to several synthetic and real-world data sets. For one, we used the data set of the European countries' financial transactions for the task of dynamic bankruptcy prediction, since the crisis hit the network at 2010. We used the window of length 2 years to build the cascade between bankrupted companies, and we predict the companies that are going to get bankrupted the next year. It can be seen that difference has a very good performance for the task of dynamic prediction. To sum up, our algorithm has the ability of identifying the underlying time-varying community structure, together with obtaining dynamic predictive distribution to use for multiple prediction tasks, such as diffusion prediction, extracting most influential users, and bankruptcy prediction. For more information, please come to our poster today. Thank you very much.